Hi class, let's get started with Module 6, the last module of this class. In this module, we'll be talking about goodness of fit. I'll explain what goodness of fit means, but let's discuss a few terms. We have what's called a frequency table. Consider a sample data consisting of observed frequency counts arranged in a single row or column. This is called a one-way frequency table. I'll show you an example in just a second. Use a hypothesis test for the claim that the observed frequency accounts agree with some claimed distribution, so that there is a good fit of the observed data with the claimed distribution. Use a chi-square distribution for goodness of fit tests. Alright, so let's do an example. A random sample of 100 weights of Californians is obtained, and the last digit of those weights are summarized. When obtaining weights, it is extremely important to actually measure the weights rather than ask people to self-report. By analyzing the last digit, we can verify the weights were actually measured, since reported weights tend to be rounded to something like, check that, something ending with a 0 or a 5. We wish to test the claim that the sample is from a population of weights in which most of the last digits do not occur with the same frequency, which would mean that they were self-reported instead of measured. Right, so consider this table. Okay, so 100 Californians were polled, okay, and we want to know, did they self-report their weights, or did they actually measure their weights? Okay, and so if an indication of self-reporting is if the weight reported was 0 or 5, the last digit of the weight reported was 0 or 5. That's an indication that they actually didn't weigh themselves, but they made up something. Okay, if the last digit is something other than 0 or 5, then there's an indication that that individual acted in good faith and actually measured the weight. Okay, so that's the problem here. We want to test the claim that the sample is from a population of weights in which most of the last digits do not occur with the same frequency. Okay, so that's the main thing here. Most of the last digits do not occur with the same frequency. Okay, so in other words, the frequency should be, there should not be a pattern. But just taking a cursory look at this data, you can see that 0 occurs with a relatively high frequency, as well as 5. All right, and all the other last digits occur with somewhat lower frequencies. Okay, so we can say then that 0 is the most frequent number, but what we want to know is this. We want to know that the proportion of each of the digits is equal. Okay, so of the 100 numbers, the sum of the numbers in the second column total 100, that the frequencies are pretty much evenly distributed. Okay, and then the alternate hypothesis is that at least one of the probabilities is different. Okay, and you can tell that 2 of them are different. But ideally, if this were an even distribution, then each of the last digits would account for 10% in frequency. So we want to test this claim. Okay, and we want to test it at alpha equals 0.05 or 95% confidence level. And we want to use a goodness of fit test with a chi-square distribution. All right, so let's talk about some notation. O, uppercase O, represents the observed frequency of an outcome, and it's found from the sample data. So these are your observations right here, the frequency observations. E represents the expected frequency of an outcome, found by assuming that the distribution is as claimed. Okay, so we would expect, if all the members of the sample acted in good faith, then each of the frequencies would be 10%. So the expected value of each of the frequencies is 10%. Okay, and K represents the number of different categories or cells. I'll show you what that means in just a second. And N represents the total number of trials. Again, I'll show you that. Okay, so null alternate hypotheses. Always state that. And so we need to construct the test statistic. And so the formula for the test statistic, the test chi-square statistic, is given by this. All right, so here's how we formulate it. I'll go ahead and show it in Excel. Okay, so for this problem, we have the last digit. Okay. All right, and so the last digit of the weights 0 through 9. So you have 10 digits, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Then we have the observations. So these are the observations from the sample. Okay, and so that would be, we have 46 for 0, 1, 2, 3, 3, 30, 30, 4, 0, 4, 0, 8, and 3. Okay, and then what do we have? We have expected frequency E, right? And so the expectation of each of the digits is 10%. Okay, we'd expect each one to occur in the same regularity for any random sample. Okay, all right. So now, in calculating the chi-squared statistic, what do we need? We need O minus E. So you see this formula right here that my cursor is hovering over. We need an O minus E. So we have O minus E. Okay. So observed minus expected. So this would equal to this value minus this value. Okay. And I hit enter. So that's 36. And then I can just drag the cell down and it'll do it for each row. All right. So we have those numbers. And now we need O minus E squared. Okay. So O minus E squared. Okay. All right, so this would equal to, oops, sorry. O minus E squared. All right, now let's try it again. Okay, so this would be equal to this number squared. All right. Let's see if I can drag it. All right, so O minus E quantity squared. All right, and so now we need to take the values, each value in this column, and divide it by the expected value. Okay, so this would be O minus E squared divided by E. Okay, and so equals this value divided by this value. Okay, so we have 129.6 for that. Okay, we do the same for each row. Okay, and so there are the numbers there. And then, okay. All right, so now the chi-squared statistic is the sum of the numbers in the last column. All right, so I can type equals sum this range right here. Okay, and so 212.8 is our test chi-squared statistic. So I'll show you in just a second how you analyze that. All right, so onto this piece. Okay, so we use a chi-squared distribution for a goodness of fit test. All right, so we have what are called critical values. Okay, and the critical values are found in table A4 for your chi-squared table, where you have k minus 1 degrees of freedom, and k equals the number of categories. So the categories are basically each of these 10 categories, the last digit. So for this problem, the degrees of freedom would equal to 10 minus 1, or 9. Okay, all right. The goodness of fit hypothesis tests are always right-tailed. That's another key point right here. And p-values are typically provided by using the Excel function chi.dis.rt, or by using the p-value website. Okay? And I put the p-value website, a link to it right here on this branch. It's hard to see in the video, but it's in your notes that I'll distribute. Okay, so now we have what are called expected frequencies. And for this problem, all expected frequencies are assumed equal, and that was the 10. Okay, all of these 10s. Okay, and so the expected frequency E is basically equal to n over k. So for this problem, n is 100, okay, because we had 100 elements in our sample, and k is 10, so E is 100 over 10, which is 10. Okay, now I'll show you later on, if the expected frequencies are not equal, then E is equal to n times p for each individual category, where p is the probability for each category. I'll have an example forthcoming. But let's just do the one case where all the expected frequencies are assumed equal, as in this problem. Okay, so let's talk about what is meant by a goodness of fit test. A close agreement between observed and expected values will lead to a small value of chi-squared and a large p-value. All right, so in this case, it's clear that there is no close agreement. So we do not necessarily have a small value for chi-squared. 212.8 is pretty large for a chi-squared value. Okay, so a large disagreement between observed and expected values will result in a large chi-squared and a small p-value. A significantly large value of chi-squared will cause a rejection of the null hypothesis of no difference between observed and the expected. Okay, so what that last statement means is that this statement right here that my cursor is hovering over will be rejected. Okay, so we're going to reject the null hypothesis that the proportions of each of the last digits are all the same. Okay, all right, and so now how do we reject that? Well, we need to find the critical value. At this point, we're using the critical value test. Okay, so we pull up our chi-squared table, and it's also in the notes, but in our case we have degrees of freedom equals to 9, and our alpha is equal to what, 0.5, right? And it's a right-tailed test, so remember in the right-tailed test you do not subtract it from 1, so it looks like 16.012, let me check, sorry, this number right here, 16.9190, 16.92 is our critical value. Okay, and so we can also get the p-value. All right, so the p-value. So the p-value is equal to chi SQ, okay, right-tailed. And then the first argument will be your test statistic, which is 212.8. And the second value will be your degrees of freedom, which is 9. Okay, and so this is your p-value. And so you compare that p-value to your alpha value, which is 0.5. And so when this is the case, when your p is low, the null must go. Okay, so the p in this case is lower than alpha, so the null must go, so we reject the null hypothesis that all the proportions are the same. Going to the critical value test, okay, the critical value situation. Okay, we look at this graph, okay. So our critical value is 16.92. It's marked with the magenta vertical line right here. And the critical region is to the right. And so our test statistic is to the right of the critical value. And so that falls in the reject region of the null hypothesis. If the test statistic fell to the left of the critical value, we would fail to reject. Okay, and so here's a flow chart that describes the process I just articulated. So there is no evenness or no similarities between observed and expected values for this problem. That's the conclusion, the technical conclusion. So we reject the null hypothesis since the p-value is small and the test statistic is in the critical region. We conclude that there is sufficient evidence to support the claim that the last digits do not occur with the same relative frequency. In other words, we have evidence that the weights were self-reported by the subjects and the subjects were not actually weighed. All right, so that seemed kind of obvious numerically. Okay, so let's go on to another class of problems. These are ones that use what are called Benford's law. So according to Benford's law, a variety of different data sets include numbers with leading first digits called LD that follow a particular distribution. So many data sets with numbers, okay, the numbers in most data sets will have the first digit distributed according to the following distribution. 30% of the numbers will have a leading digit of 1, 17.6 of the leading numbers will have a distribution of 17.6, and so forth. Okay, so let me show you an example of an application of Benford's law. Bear in mind that this would be a case where the expected frequencies are not the same. Okay, so this is going to be this case of the branch. The first problem we just did, the expected frequencies were all the same. In this case, the expected frequencies of the data are going to follow this distribution, and you can readily tell that the distribution is varied, not all the same for each digit. All right, so here's how it works. The bottom row lists the frequencies of leading digits of the populations of all 120 counties from New York and California combined. Test the claim that those 120 counties have populations with leading digits that follow Benford's law. Okay, so our null hypothesis is that the leading digits do follow Benford's law. Okay, so they do follow Benford's law, and the alternate hypothesis is that the leading digits from New York and California do not follow Benford's law. All right, so here's the data. Leading digits of populations from New York and California counties. All right, so 33 counties from New York and California, the populations start with 1. 22 counties from those two states, the populations start with 2. 10 counties from those two states, the populations start with 3. Okay, and so forth. And then, like in the last column, 9 counties from New York and California have populations that begin with the digit 9. All right, so we go ahead and construct Benford's table. All right, so I can do that in Excel using the data. So let's go to another sheet. If it'll let me. There we go. Eventually let me. Okay, so we have leading digit. All right, and so the leading digit will be 1 through 9. Okay. And what else? We have the observations. Okay, so observations. So 33 counties in both states have populations that start with 1. Okay. 22 counties have populations that start with 2. 10 counties have populations that start with 3. 15 counties have populations that start with 4. 10 counties have populations that start with 5. 9 counties have populations that start with 6. 5 counties have populations that start with 7. And 8 counties have populations that start with 7. And 9 counties have populations that start with 9. Okay, and then we can put Benford's percentages in. We'll wire those up. So Benford's percentages, so we'll call these BPs. Okay, so this would be 0.301. Okay, 0.176 for 2. Okay, 176.125 for 3. 0.097 for 4. 0.079. Let's see, 079 for 5. 067 for 6. 7 is 0.058. 8 is 0.051. And 9 is 0.046. Okay, so where did these numbers come from? So again, let me show you in the Word document. They came from this table right here. Okay. All right, so the next thing we want to do is we want to compute the expected values. So the expected values is equal to O times the Benford percentage. So E is equal to N, okay, or these are your N values right here. These are your percentages, so this would be O times BP. Okay, so this would equal to your expected values, so this would be this number times this number. Okay, so we have that. Oh, I'm sorry. Oops. No, I'm sorry. I beg your pardon. Those are observations. N is the number of counties. I beg your pardon. N. This would be, I'm sorry, I gave you the wrong formula. I was looking on the wrong page. E is equal to N times P, where N is the number of counties. So 120 counties. I'm so sorry. Okay, so this would be equal to 120. Do it. I'm going to go ahead and put N so I won't get confused. So N is equal to 120. And I'll go ahead and repeat this value for the rest of the column. Okay, now E is equal to N times P. These are your expected values for each digit. Okay, the expected value. So this would equal to Benford's percentage times N. Okay, so we do all that. Okay, so those are our expected values, which look about right. Okay, now we calculate our O minus E, just like we did with the other table. The only thing we did differently is we had to calculate the expected value. So O minus E, okay, so that would equal to this value minus your expected value. Okay, and so that's 29.28. No, that's not right. That can't be right. Observed Let me check again. This does not look right. 120 n times p. 120 times 031. Oh, no wonder. That should be 0.301. Sorry, I don't know decimals. All right. Okay, so that's equal to this times this. Okay, 36.12. That looks better. All right. Okay, had an error in that first cell. Okay, so now we have this is equal to O minus expected value. Okay, so minus 3.12. Good. And now we just repeat. Okay, so those are our O minus E values. Now we take that column and we square each of the elements. So this would be O minus E squared. Okay, so basically I take that number and I square it. Okay, and then I bring this down. And then I take that column and I divide it by the expected value. So O minus E squared divided by E. Okay, so this is equal to this value divided by that. Okay, and so to get our chi-squared statistic, that would equal to the sum of the glass column. All right, so our chi-squared statistic is 5.4 for this. It's a little bit different than what's in the notes. Okay, so we can get our p-value. Right tail chi-squared, right? So that would be chi-squared RT, and our test statistic, which is that number, and the degrees of freedom. Okay, so what are the degrees of freedom? Well, we have 9 members, so the degrees of freedom would be 9 minus 1, which is 8. Okay, and so our chi-squared statistic is 0.7. So the reason why it's different from the notes is, in all likelihood, I made a data entry error. I'm not very good at data entry, so go back and check all of these numbers, 12, 5, 1, 7, 6, yeah. Perhaps there's an error somewhere. Okay, well anyhow, we can still press forward with this. The method is still the same. Okay, so we have our test statistic here and our chi-squared statistic here. And we want to, well, since our alpha is 0.5, this number is bigger than alpha 0.5, so we fail to reject the null hypothesis. Okay, and the null hypothesis is that the 120 counties have populations with leading digits that fit Binford's law. Okay, in other words, there's insufficient evidence to support the claim that they do conform to Binford's law. Okay, so that's the p-value test, and then we can use the chi-squared against the test statistics. So we have what? We have right-tailed chi-squared with what? Degrees of freedom 8 and a test statistic of about 5.4. So let's look at degrees of freedom 8, and alpha is what? 0.5. So that gives us a critical value of what? Let's see, 15? What is the 13? The book has 13. I'm not sure where they're getting that from. Let's see. Alpha 0.5, yeah, 15.507. So it looks like the notes flipped looks like they transposed 15 to 13. So this is your chi-squared statistic. So we'll make the correction in the notes. So 15.507 is your critical value, and so the critical value, your test statistic falls to the left of the critical value, right? And so that's in the region where you failed to reject the null hypothesis. All right, so that's one example of a expected value where you don't have a normal you don't have an even distribution of the probabilities. Okay, so what's next? Go back to the Word doc. An investigator analyzed the leading digits of the amounts from 200 checks issued by 3 suspect companies. The frequencies were found to be 68, 40, and so forth, and those digits correspond to the leading digits of 1 through 9 respectively. Okay, so if the observed frequencies are substantially different from the frequencies expected with Binford's law, the check amounts appear to be the result of fraud. Okay, use the O5 significance level to test for goodness of fit with Binford's law. Okay, so what are the null and alternate hypotheses? Okay, for this problem. Okay, so well, okay, so we want to calculate the chi-squared statistic. So there's really not a per se a okay. So well, the null hypothesis is what? That that there is fraud, right? That the okay. So let's see. Read it again. If the observed frequencies are different from the expected frequencies from Binford's law. Okay, so the null hypothesis is that I should write this down. Null hypothesis. Okay, check numbers conform to Binford's law. Okay, and if that's the case, then there's no fraud. Okay, so it would be no fraud. Okay, and then the alternate hypothesis is, well, check numbers do not conform. Okay, and fraud. There is fraud. Okay. All right, so we need to, so if we fail to reject the null hypothesis, there's no fraud. All right, so the solution goes like this. Okay, so in your first column, you list the check numbers. Then in the second column, you list your observed frequencies. So these numbers right here. Okay, for each check number, you have the frequency. So check number 1 occurred with the leading digit of the checks. The leading digit of all the checks, 68 had a leading digit of 1. Of all the checks, 40 had a leading digit of 2. 18 had a leading digit of 3, and so forth. So of all the checks, 12 had a leading digit of 9. Okay, so here are the expected values. Again, the 60.2 is 68 times what? 30.1%. Okay, the 35.2 is 40 times 17.6. Okay, and so forth. So the 12, all right, no, I'm sorry, check that. The 9.2 is 12 times 4.6%. Okay, so those are your expected values. Then we do the O minus E column. Okay, yeah, 200 checks, right? Okay, all right, just checking. Okay, and then O minus E squared is this column, and then O minus E squared divided by E. So our chi-squared test statistic is 14.432. So again, for degree freedom 8, alpha 5, chi-squared is 15.507. So this number 14.432 is to the left of this critical value, and so we fail to reject a null hypothesis and conclude that there is no fraud. Okay, so all right. So is there sufficient evidence to conclude that the checks are the result of fraud? There is not sufficient evidence to warrant rejection of the claim that the leading digits are from a population with a distribution that conforms to Binford's law. The check amounts appear to be legitimate. Okay, so they do appear to conform to Binford's law, which is kind of a random distribution in a sense. Okay, so the next topic. Let's talk about contingency tables. All right. So a contingency table, or two-way frequency table, is a table in which frequencies correspond to two variables. One variable is used to categorize rows, and a second variable is used to categorize columns. Contingency tables have at least 2 rows and at least 2 columns. Okay, so you're going to have 4 cells. All right, so so let's do an example of how you analyze a contingency table. Okay, so the contingency table, and I'll tell you what it's used for. The example will reveal that. So below is a contingency table summarizing the results of foot procedures as a success or failure based on different treatments. So surgery had 54 successes and 12 failures for the same foot procedure. So all of these remedies were for the same foot ailment. Okay, so a foot ailment was treated by 66 surgical cases, and 54 were success, 12 were failures. There was a weight-bearing cast applied to the foot, the same foot ailment, 41 successes, 51 failures. A non-weight-bearing cast for 6 weeks applied, okay, 70 successes, 3 failures, okay, for the same foot ailment, okay, and then non-weight-bearing cast less than 6 weeks, okay, and there were 17 successes and 6 failures. Okay, so we want to test the independence, okay. So what the independence means is that no one procedure was more effective than the other. Okay, so a test of independence tests the null hypothesis that in the contingency table, the row and column variables are independent. Okay, so in other words, if that's going to be the case, then no one treatment is better than the other, essentially. Okay, so O represents the observed frequency in a cell of a contingency table. E represents the expected frequency in a cell found by assuming that the row and column variables are independent. Okay. R represents the number of rows. C represents the number of columns. Okay, so the null hypothesis is the row and column variables are independent. Alternate hypothesis is that they are dependent. And our test statistic, again, is a chi-squared test statistic. The expected value is the row total times the column total divided by the grand total. Okay. O is the observed frequency in a cell, and E is the expected value. Okay, so E is the expected value. All right, and here's the formula for the expected value. All right, so p-values and critical values for contingency tables. So again, for p-values, we use the chi-square.dis.rt. We plug in our test statistic and our degrees of freedom. So I'll show you how to calculate the test statistic of a contingency table in just a second. But the critical values, again, are found using the degrees of freedom of row minus 1 times column minus 1, right? So this is a quirky formula for degrees of freedom. And it's always a right-tailed test. Okay, so expected value. All right, so for this particular table, okay, the expected value is basically what? The row total. Okay, for surgery. Okay, for surgery that is. All right. For surgery, the expected value is the row total, which is what? 66 times the column total, which is the sum of these numbers. Okay, see surgery is here. Okay, so the column total is what? Okay, so how do we know which column to use? That's an interesting question. Well, since we're interested in successes, which method is successful, in other words, we're trying to test the claim, analyze whether one treatment method is more successful than another one, we can do this one. So we'll do this type of analysis. But if we were interested in which treatment had more failures, then we would use this column as the column total. Okay. So we want to test the theory that one method of treatment was more successful than another method. Okay, and then the null hypothesis is that all the methods of treatment are equally distributed. That no one method is more successful than the other. Okay, and so that would mean that each one is independent. All right, so successes, that's what we're analyzing. So you sum these numbers, and that's 182, and then you sum all of the numbers. Okay, all 8 numbers to get the grand total. So the expected value for surgery is 47.478. All right, so I guess we could go ahead and can we build the contingency table for this? Would it be instructive? Let's do that. It's not in the notes, so I guess we should do it here in the video. Okay, so let's pull up Excel and calculate our test chi-squared statistic. All right, if it'll let me. All right, so we have treatment. Then we have what? Success. And then we have failure. Okay, and so the treatment mode was surgery. Okay, the second treatment mode was cast, weight-bearing cast. Okay, the third treatment was non-weight-bearing cast, non-weight-bearing cast for 6 weeks. And then the fourth treatment mode was non-weight-bearing cast, non-weight-bearing cast, less than 6. Okay, so those are the codes for treatment codes. Okay, and so our success was what? 54 for surgery. The next one, 41. The next one was 70. And the last one was 17. Okay, all right. Then the failures were 12, 51, 3, and 5. All right, so that's our data. All right, so now we can sum up all the numbers, okay, because that'll be used everywhere else. Well, let's see. So we know that the sum of all the numbers would be this, oops, equals sum. This number, 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 this number. Okay. Okay. So 8 numbers, right? So our sum is 253. Okay, so that checks. Okay, so we can get the expected value. Okay, so E, right? Well, let's see. We need row total for surgery. Okay, so for surgery, okay, so the expected value would equal to row total times, let's see, sorry, that would equal to the sum of row total times the sum of the column total divided by this number. Okay, so that's 47.478, which agrees with the notes. Okay, can I duplicate this? Let's see. No, it won't let me. Okay. So those are the expected values. Okay, so the expected value for the second treatment mode would equal to sum of the row times the sum of the column divided by the total, which is 253. Okay, and let's see, the expected value of this would equal to the sum of the row times the sum of the column divided by the total. Okay, and then the expected value here is equal to the sum of the row times the sum of the column, okay, divided by this. Okay, so those are our expected values. Okay, so now we need our O values. So the O values, of course, are the successes. All right, so we need our O minus E. Okay, so this would equal to observed minus E. Okay, and so let's see, observed minus E. Okay, so we drag that down. Okay. Let me see the expected value over here. Is that right? Let me check. I have a discrepancy here. Let's see, they say 6.174. So what is wrong here? The row total, which is 22. Let's check. Row total, which is 22, times the column total, which is 182, divided by the grand total, which is 253. Yeah, that looks to be about right. Okay. All right, well, let's proceed. So now we need O minus E squared, right? So O minus E squared. So that would equal to these numbers, the numbers squared. Okay. Okay, we have those. And then we have to divide them by E. So this would be O minus E squared over E. Okay, so this is equal to this number over this number. Okay, so 8, 9. All right, and then drag those down. Okay, and so I'm not sure if that's right. It looks like it's considerably different. I'll have to check. All right, so the (54, 6). Okay, so we square it. Okay, divide it by E. Looks a bit odd. Okay, well anyhow, this will equal to sum. So this will be our chi-squared test statistic, which is 16.38, which differs from the notes. So why is that different from the notes? For surgery. Okay, let's check. 54. So 5. Where did they get 5? They did a failure? They used failure? Minus. So they said there will be 8 of these calculations. Oh, okay. So how many we did? We only did half the calculation. So I guess we do have to do the expected value for surgery. So the chi-squared statistic will also have to incorporate the failures as well. The expected value of surgery. It's a little bit odd. Okay. So we do have to incorporate. So these were for the successes. All right. I'm reading through the notes here. Okay, so let's do the expected values of the failures. So these we did the successes. So now we need to do the expected values of the failures. So we'll call these EF. Okay, so this would equal to the sum of the row. Okay, so for surgery, the expected value of the failures would be sum of the rows, okay, times the sum of the failure column. Okay, it'll be that divided by 253 again. Okay, so that's the expected value of the failure, expected value of the success. Okay, And then we do the same for this treatment mode. So this would equal to the sum of the row, okay, times the sum of the failure column there, divided by 253. Okay, and then the failure expected value of the failure of this treatment mode would equal to sum row times the sum of the column divided by 253. Okay, and then this would equal to the sum of the row times the sum of the column divided by 253. Okay, and so now we sum up the expected value. Okay, well, let's see. No, wait. Okay, so now we need the observed. Okay, so observed failures minus the expected failures. Okay, so we'll have that. So this would equal to that number minus the observed failures minus the expected failures, that number. Okay, so we have that. Okay. All right. Okay, so, and then we square that. So this would be OF failure, okay, OF minus EF quantity squared. Okay. All right, and then we take that OF minus EF squared, and then we divide it by EF, which is EF, right? Okay, so this would equal to this number divided by expected. All right, and so we do all that. Okay. All right. Okay, so that seems okay. So now we sum up the failure column. So this would equal to sum of these numbers. Oops, sorry. Equals to sum. Come on. Okay, and we get 42. Okay, so now the total chi-squared test statistic would be the successes plus the failures. So this would equal to sum of this number plus this number. Okay, and so that should agree with the notes now. All right, so failures and successes and failures have to be processed. Okay, so the null hypothesis is, again, the choice of treatment is independent. Okay, so no one treatment method is better than the other. And then the alternate hypothesis is that one treatment does prevail. Okay, all right, so now, what is our critical value? So let's go back into our notes and look at the critical value. So the critical value is determined, so we have 4 rows, 2 columns, right? That comes from this. Okay, we have 4 rows and 2 columns. Okay, 4 modes of treatment, success or failure. Okay, and so R minus 1 is 3, C minus 1 is 1, so the degrees of freedom are 3, and the chi-squared for alpha, so we have 3 and 05 is right here, 7.81. So our critical value is 7.81. So 58.39 is to the right of 7.81. So we reject the null hypothesis that all treatments are independent. So we accept the alternate hypothesis, okay? And so the alternate hypothesis was that one treatment prevails. Okay, so we reject. It's in the rejection region. And so here's the interpretation. It appears that success is dependent on the treatment. Although the test does not tell us which treatment is best, we can see the success rates of 81%, 44, 95, and 77 suggest that the best treatment is to use a non-weight bearing cast for 6 weeks. Okay. All right. So that was a contingency table example. All right, so let's do an example. Okay, so alert nurses at the Veterans Affairs Medical Center in Northampton, Massachusetts, noticed an unusually high number of deaths at times when another nurse, Kristen Gilbert, was working. Kristen Gilbert was arrested and charged with 4 counts of murder and 2 counts of attempted murder. When seeking a grand jury indictment, prosecutors provided a key piece of evidence consisting of the table below. Use a 0.01 significance level to test the defense claim that deaths on shifts are independent of whether Gilbert was working. Okay, so the null hypothesis is that the deaths are independent. Okay, the alternate hypothesis. Okay, so the null hypothesis is not guilty. The alternate hypothesis, okay, proof of guilt, right? That when she was working, there was a disproportionate number of deaths. Okay, and ostensibly she did them. All right, so when Gilbert was working, she had 40 shifts with a death. Okay, and there were 217 shifts without a death. When Gilbert was not working, there were 34 shifts with a death and 1,350 shifts without a death. Oh my goodness. I can just tell by the proportions that when she wasn't working, there were very few deaths. But when she was working, man, quite a few. So, all right, so for all you criminal justice majors, take note. Okay. All right, so here's our contingency table. Gilbert was working, okay. Gilbert was not working. Here are the shifts with a death, shifts without a death. The row totals, column totals. Okay. So the observed values, here are the observed values. Okay. The expected values. All right. So how do we get this expected value? Well, this 31, I guess maybe I can work through it in Excel. Before I do that, why don't I write down the null and alternate hypotheses? Always start off with your null and alternate hypotheses. Okay, so the null hypotheses are death rates are the same. Are independent, whether Kristen was working or not. I don't think there's anyone in our class named Kristen, so that's nice. Okay, death rates are independent, whether Kristen was working or not. Okay, not guilty. Okay, and then the alternate hypothesis. Okay, death rates are dependent. On Kristen's work. Guilty. Okay, so let's see. All right, so here's how a juror should handle the case. Okay, so let's wire up our table, our contingency table. All right, so we have shifts with death. Okay, Kristen was working. Not working. Okay, so the shifts with death will be here. So that would be 40 shifts when she was working, 34 shifts when she wasn't working. Okay. No death. Shifts with no death. Okay, so there were 217 shifts she worked where there were no deaths, and then when she didn't work, there were 1,350 shifts where she didn't work where there are no deaths. Okay, so now the totals here would equal to the sum. So we're basically calculating our chi-squared test statistic. Okay. And so the totals here would equal to so those are our totals. Okay. So we have observations, so we have 40, 34, 217, 1350. Okay. So the expected value here would equal to the, for 40, it would equal to the row total times the column total divided by, well, I need to sum up all these numbers. Sum of that number, that number, that number, and that number. Okay, so 11.59, okay. So for 34, it would be, the expected value for 34 would be 1384 times the column total, which is 74, divided by this, the grand total, which is that number. Sum. Let me go ahead and make the sum separate. Okay. Sum. Let's go ahead and get the grand total. This number, this number, this number, this number. So our grand total is that. Okay, so it's 1641. Oops, messed that one up, didn't I? Okay, so this would equal to 74 times 1384 divided by 1641. Okay, 62, and then this would equal to, for 217, it would be, row total is 257, column total is 74, divided by grand total, which is 1641. Okay, and then for, it doesn't look right, it would equal to that number times that number divided by that number. Okay, that looks better, 245. Okay, and then for the expected value of 1350 cell, that would be equal to that number times that number divided by that number. Okay, okay, 1321. Okay, so expected and observed are almost the same, as well as for 1350, and expected and observed is almost the same for 217. What's concerning is that the observed value is 40 when the expected value is should be 11.6, so that should raise a flag. All right, so O minus E okay, this would equal to that value minus that value. Okay, and then O minus E squared okay, so that would equal to that squared. Okay, and then O minus E squared over E. Okay, so this would equal to that divided by that. Okay, so we have those numbers. All right, and then our test statistic would be the sum. Sum. Here is our test chi-squared test statistic. Okay, so it's 86.41. Okay, so what are our degrees of freedom? So it would be right here. Row minus 1 times column minus 1, so that's 1. So our degrees of freedom are 1, and alpha is 0.5. So the critical value is 3.84. No, I'm sorry. I'm sorry. Our alpha is 0.1. So our critical value is here. Our critical 6.639. So in this case, we failed to reject the null hypothesis because 86.481 is bigger than 86.6. So it's in the reject the null no, in this case we reject the null hypothesis because our test statistic is to the right of our critical value. So we reject the null hypothesis. And so when you reject the null hypothesis, we accept the alternative hypothesis that death rates are dependent on Kristen's work. She's guilty. And that's not a type 2 error. Okay. All right. Okay, so what next? Is there sufficient evidence to reject the defense claim that deaths on shifts are independent of whether Gilbert was working? There is sufficient evidence to warrant rejection of the claim that deaths on shifts are independent of whether Gilbert was working. The results favor the guilt of Gilbert. Okay, so for all you criminal justice majors, now you have a reason to know statistics. Okay, okay, so that ends all the content, the lecture content. So we need to prepare for your final exam, and your final exam will consist of 30 questions. Okay, the final exam will be comprehensive, and during the live lesson, you'll have a chance to ask questions. So at the end of this document are 30 review questions you should go through. So some of the questions, I can start with, like, for instance, question 30 is treats the topic that we just went over. So let's go to question 30. A researcher wishes to test whether the proportion of college students who smoke is the same in 4 different colleges. She randomly selects 100 students from each college and records the number that smoke. And here are the results. Okay, so what do we want? Does it ask? Okay, so she wants to test whether the proportion of college students who smoke is the same at all 4 colleges. Okay, so in this case, how many people are we testing? 100 students, okay? So this would be an example of testing proportions. Okay, so we need to formulate the null and alternate hypotheses. All right, so the null hypothesis is that the proportion of smokers is the same at all 4 academic institutions. Okay, so we need to calculate our chi-squared test statistic. And then the alternate hypothesis is that at least one proportion is different. All right, so let's go into Excel and do this. All right, so let's open up our Excel. Okay, new sheet. Okay, so the way this would be stood up is we have okay, so we would have, so our table goes like this, right? We have college A, college B, let's see here. Well, I think there's an easier way to set up the table. So we have, let's do this. We'll put the college here, okay? So we have what? A, B, why didn't B type? B, C, D. Okay. All right, so there's a college, and then we have smoke and non-smoke. Okay. All right, so for the smoke, A, it was 17 and 83. 17 and 83. And for the B, it was 26 and 74. 26 and 74. C, it was 11 and 89. And D, it was 34 and 66. Okay, so let's do the expected. Okay, so these are the observed values for smoke. So let's do the expected values for smoke. Okay, so this would equal to what? The row total, which would be sum row total divided by the column total, which is that. Okay, it would be, I'm sorry, it would be product, not the division, quotient. Sum of row total times the sum of the column total divided by the grand total. So that would be the sum of these numbers. Okay, so that's the expected value of the smoking at college A. Okay, so it's a little bit greater than the observed value. Okay, so, all right. And so what do we need? We need ES, O minus ES, right? Observed minus ES. Okay, so that would equal to this number minus that number. Okay. Okay, and then we need O minus ES squared. So O minus ES squared. So it equal to that number squared. Okay, and then we need O minus ES divided by ES. So O minus ES squared divided by E. Okay, and so that would equal to this number divided by ES. That should be, sorry, that should be an ES. We need an ES there. Okay. So that would equal to O minus ES. Still don't have it right. Come on. It's not letting me. O minus ES squared. Okay, there we go. Alright, so this would equal to that number divided by that number. Okay, so we have 198. Okay. Alright, so that would be for smoking, and then we do the same for non-smoking. Alright, so we would have the expected value of non-smoking. Well, okay, yeah, expected value of non-smoking, so that would equal to sum of the row times the sum of the column, which is this, divided by the sum of everybody, the grand sum. Okay. Here we would have the sum of the row times the sum of the column divided by the grand total. Okay, and then here we would have the sum of the row times the sum of the column divided by the grand total, the sum of everybody. Okay. All right, and then I suspect the last value will be 78 as well. Okay, so this would equal to the sum of the row times the sum of the column divided by the sum of everybody. All right. Okay, so now, interesting. So now we need O minus E, O minus En, right? So that would equal to observed minus En. Okay, and so, okay, and then we need O minus En squared. That would equal to this squared. Okay, and then we need O minus En squared over En. Okay, so that would equal to this, okay, it would equal to this number divided by En, 78. Okay, so now we need to sum what? These numbers. We'll sum, okay, and we need to sum these numbers. That'll give us our test statistic, which is 599. Almost 600, right? So our test statistic is almost 600. So what is our critical value? So our critical value is number of rows minus 1. So we have 1, 2, 4 rows. So 3 times 1. So our degrees of freedom would be 3. Number of rows minus 1 times the number of columns minus 1, which is 3. And then our alpha is 0.5. Okay, so we need to go to our chi-squared table. So 3 and 0.5. So our chi-squared critical value is 7.18. So 600 is definitely to the right of that. And so being to the right of the critical value in a right-tailed test means we reject the null hypothesis. Okay? And so the conclusion would be at least one of the proportions is different. Okay? And so you can check. My guess is that college D is in delta has greater than 50%, whereas all the other colleges are running at about a third or a fourth. Okay, much less. So college D is probably the one that stands out. But we don't know. Further investigation is warranted. So that's question 30. Okay. Okay. All right, so that's 30. Okay, so what next? Okay, so question 29. What is question 29? Use the given data to find the equation of the regression line. Okay, so we have a regression line problem. Again, you can use Excel to do that. All right, so the data are, so we have x, y. Okay, and so our x values are 1, 3, 13, 1, 3, 13, 7, and 9. Our y values are 143, 116, 100, 98, and 90. Okay, and so we need to do a regression. So we go to data, right? Data analysis. Okay, or we can just do a chart. Why don't we just do a chart? So we can do an insert, scatter chart, Okay. Oops, I have to Control Z. We have to select the data first, right? Insert, scatter plot. Okay, yep. And then just right click on a point and add a trend line. Okay, and then with the trend line, what do? We can display the equation on the chart, and so there it is. So that looks like it's choice B as in boy. Okay, which is given. Okay. So what about question 28? Use the given information to find the coefficient of determination. Find the coefficient of determination given that the value of the linear correlation coefficient is minus 0.721. Okay, so the coefficient of determination is r squared. So you just square the number. Okay. And then what else? Question 27 was from a previous quiz. Okay, so you should have that one. All right, and so for the rest of the questions, what I'm going to do is I'm going to save that for the live lesson. So what you guys should do is you should look over the questions from the handout and then bring them to our live lesson lecture. And then if there are any ones in particular you wish to work out, we can go over that during the presentation. Let's see, I'm just looking at a few. Okay, if there's anyone that stands out. All right. Okay, so that will be it for the recorded videos. So I will see you all during the live lesson.